Switch? Not on the sides anymore. Yeah, I went full screen. Yeah. I don't know. Hang on, wait a minute. This goes to this. All right, well, thank you, ladies and gentlemen. My name is Dave Valentine. As you can tell from the extremely thick accent, I'm not from around here. I'm from Canada. And I'm joined today with William,
also known as S-Tech.
And we're doing a co-presentation on 4 kilobyte intro development, which is actually kind of a unique thing because I have done presentations before on 4 kilobyte intro development. And this is a nice way for us to have two different views on the same subject. It is a technical talk, but I'm hoping that I can put it in some non-technical terms for you, for anyone that has it. Also, we have a fairly small group here. I have demo sceners in the group, and I'm hoping there's some that are demo sceners that don't know they're demo sceners yet, as Jason would say, right? So with that, let's get it a little bit interactive, ask some questions or what have you, and we'll try to address them throughout the talk.
Very good.
Okay. So first of all, just a presentation overview. We're going to talk about who we are and what are 4 kilobyte intros. We're going to show two intros today. One is called in 4K. The other one is Parsec. We're going to do then an evolution of size reduction techniques so that if you're contemplating creating 4 kilobyte intros, that you can see how there's been a sort of a chain of techniques that have been used to reduce size, and it's evolving over time. And then we're going to show the end result of a 4 kilobyte framework which we put together and to demonstrate sort of just what goes into creating some 4Ks. All of this will actually be put into a website, and we'll put a package on that website. So the files will be made available, and if you have any questions about those or what have you, you can always access them from that site. And again, this presentation is not meant to be exhaustive, but an overview. There's a lot of things we had to skip, and we figured we could do at least a one-day seminar on all of the 4K, not just much less an hour. So again, as I mentioned, I'm Dave Valentine. I'm the founder of the Northern Dragons, which has now entered its, just past its 6th year of existence, so it's now on to year 7. I've traveled here from Winnipeg, Canada, so for anyone who's native to Cleveland, I know snow as much as you do. So that's something I can say. Also, I was the co-founder of the In4K site, which is probably the largest web portal or wiki which is used for 4 kilobyte intro development. And the information on that wiki is actually very, very helpful. And we have a number of contributors. It's supported by a very small scene, so we haven't seen those scalability options that Jason Scott was mentioning earlier. But I will say that our Wikipedia entry about the Northern Dragons has it founded by Polaris, Loopy, and Hawk, which is wrong. I don't know, I was there. I don't remember Loopy being involved, but we're trying to correct it. So I've also written a number of intros, including Trees, the Ethereum. I should actually say I've collaborated with a number. Trees I wrote all on my own, but the Ethereum Forest I wrote on my own, Levucio, Blobzilla, In4K, and so forth have been collaborations with a number of people, sometimes in remote geographies. And I do have a personal message for Sesame, somebody that I'm anticipating meeting sometime in November. So it's a thing. And okay. As I mentioned, I'm from Winnipeg, Manitoba. Anybody know where that is? No? Okay. So Winnipeg is just north of North Dakota. We have a small population in the city, about 600,000, about 650 if you round up kind of thing. However, it does have a thriving digital arts community. So we've established a local international game development chapter. There is a game studio that has recently started as an incubation project in association with the Manitoba government. And it's really out there in order to promote the game industry, to assist people in their product from idea to out the door. So as time goes on, Winnipeg and Manitoba may not be known as just the city that forced the game industry to put the T for teen ratings on the box, but also as a thriving game development community. So maybe at some point there'll be somebody from Cleveland saying, "What's Cleveland about?" in Manitoba, giving a speech something like this about the game industry. And Aztec.
All right, well, I'm Aztec. I wrote a lot of demos. I first joined up with the Northern Dragons when I first joined the scene. I worked on the Ethereum with them. I also did 0x0f, which was a 16-byte demo. It's just 16 bytes. It was really sucky, but I mean, hey, a waterfall of color and 16 bytes, how can you beat that? I worked on Zero with the Northern Dragons. Then I went off on my own, started a group called Trailer Park Demos along with Tom, another scener who's in Canada. And we produced I.O. and also producing one that we're going to release here. California's nice, no snow, 60 degrees all year round, but it's boring, so that's why I'm a demo scener. All right, let's go ahead and move on.
Okay. So this is from the old school demo scene FAQ, which may and should look familiar to a few of you. But basically, an intro is really a demo program which displays sound, music. It's a light show, usually in 3D. And they're much because you get this sense of awe. Back in the day when you had sort of, or if you were attending Trickster's program earlier today, you look at this machine and you have these almost drunken-like bets saying, oh, well, I can make it display 256 colors in this mode, or this or that or the other thing. And you end up pushing that machine beyond its limits. And so, it's sort of, you go to a demo party, you get this sense of awe. And it's an evolving art form that blends mathematics, programming skill, creativity into something that's beautiful to watch and listen to. And as the technology has increased, we've focused less and less by the means of doing what we do and more into what we're actually doing. And you also see that in things that, such as the 4K intro. But the real thing with the 4K is that it is a demo, okay? Music, sound, graphics, but it means that you do it in 4 kilobytes or 4,096 bytes. So the machine that, when you think about it, right? I mean, that's 4,096 characters. That's it. You could print that on a couple pages. The interpreter, the command line interpreter inside DOS is closer to 32 kilobytes, right? Windows itself, you need a CD that's 750 megabytes or 700 megabytes in size, right? If not, for the patches, you need to download an entire DVD's worth. So this is really sort of the area where somebody can go in and focus on something fairly small and still have a technical edge to it, but try to make beautiful art. And why do people make them? Well, they make them to the same reason why they make demos, to show off, show the hardware's capabilities, show their creative abilities as musicians, and to show the programmer's abilities with 3D. And the goal, as always, is to impress, especially in 4K. Now, one thing which I will mention from naive experience is that the Dragons, when I founded the Dragons, we planned to go to Assembly, which is a very large European, based in Finland, demo event. So we founded the group, we made the trek, we didn't finish our demo, we released it anyway, in one of those, hey, we were here kind of moments. And the following year was probably the most critical in the history of the Northern Dragons, because at that point it's like, okay, we came, we saw, we went, we didn't get much done, but it was fun. What do we want to do now? And we decided to work on a 4K because, hey, it's only like a couple pages of code. How hard can it be, right? Well, 4Ks are extremely sophisticated, and it led into a growth of it, because at that time it was not very common to have music, and then we saw music getting added, then more and more features, and so on and so forth. And the objective of the talk is to give you a background on this type of development so you'll have some idea about how to make them, if you so desire. The first demo viewing that we're going to do is one of my selections. I guess you could call it a shameless plug. This was released at an event. It was released at the Pilgrimage event in 2005. So that means that at this point it's 2 years old. The music is quite nice, and I'm hoping that it will show up when we hit the next button. With that music, It was actually composed by someone in Finland, so this was a collaboration between Canada and the Finns in order to create. And In4K, again, is a site dedicated to talking about the development of 4 kilobyte intros. So let's give it a shot. Okay, I'm not hearing anything. Okay, hang on. Hang on. Of course, now you don't see anything. All right, hang on a minute. Okay. Yeah, we had the brilliant idea of one of the things that happens often in 4 kilobyte intro development is because you're trying to reduce the size, you end up doing all kinds of tricks, right? And we decided to render everything to video so that we wouldn't have the projector suddenly have a heart attack when we showed one of these productions. And of course, when I do that, it means that I have to remember that video files don't always like to be played on 2 screens at once.
That was only 4,096 bytes, which is pretty impressive, right? We got particle systems, you got music, you got text. This next one I selected because I think it represents probably the state of the art. What is possible for insane geniuses, and I don't know how they're human or anything, but this is what you can do in 4,096 bytes if you really try. jerky playback ruining the vibe. If you actually run the real demo, it's actually smoother than this playback of a video, and it's smaller. So, so that's what's possible.
Yeah, it's a gargantuan difference in size. I don't know what happened with that playback. We had tested it before. So go check it out. Go to puit.net. Type in parsec. There's 2 productions. One's 4K. You'll know which one. So with our talk here, we're going to talk about evolving reduction. And the way that we're going to do this is that we've taken a source application from nehel, from nehel.gamedev.net, which Jeff has up there a number of OpenGL tutorials. I think he's up to like 35 now of various subjects. And we've taken a very simple one, which has a rotating cube and a rotating pyramid, a 4-sided pyramid, that as a sample. And we're going to show you a variety of techniques to bring that down as far as we know we can go. We actually had done the presentation, then I was in the airport and managed to start to fuddle with some other ideas, and we've since being here have made some other optimizations that STech will talk to as well. So if you take that and you download it and you stick it in a compiler, the output is 11K, basically. Now, you're sort of sitting there saying, okay, wait a minute, Dave. We just saw a production with this huge sphere, this beautiful scene with particle effects, with what probably has pixel shaders. I don't know the internals of it, so I can only guess. And yet, to display a cube and a pyramid, flat shaded with some coloring, it already takes 11K out of the box. How the heck is this possible? So we're going to show 2 overall approaches. One is to talk about some OS-based techniques, which are really more about how to represent your program and your code environment. And then we're going to look at algorithmic. So one is inside the box, right? That's more what are we doing, how are we representing this. The other one's outside the box type of approaches. And all the presentation files, as I mentioned earlier, will be made on in 4K. So what are we trying to do? Well, you're trying to make a very small program, really, an executable image. And before you can really intelligently think about that, you're going to have to find out what an executable image actually is. Now, I know that there's the ELF format for the Linux gurus in the group. I'm not a Linux guru. However, some of the things that I will show apply to Linux, so I'm going to be talking mostly about the Win32 format. The Win32 format in Windows executables is the PE format, or portable executable format. And it's similar to the COF format or the ELF format. And you can see that you have a header, stubs, another header, a section table, and then a whole bunch of sections. Now, the header, the first one is the DOS header, which basically says, congratulations, you have tried running this program on this DOS program or a Windows program in DOS. And so it basically says, hey, you can't run this program. So it's a legacy thing that's in all executables by default to say, you know, sorry, you don't have Windows. Too bad for you. And the PE header holds the standard structures for the PE loader, and then you've got the section table. And I want to stop you from thinking that, oh, okay, I've got code, I've got data, and these are different sections, because they're not. The only thing that really puts things into various sections is its attributes. Can it be read? Can it be written to? You know, it's more of a question of what are the rights of storing that data that decides whether it's in a section or not, as well as your standard compiler options. So the sections hold a block of data. These can be anything, right? API functions, they can be imports, values, variables, and so forth. So they have a chunk of data, and there's nothing that prevents them from being in the same section. And one of the first things that you may do as someone who's interested in 4K intro development is actually merge those 2 sections together. The compiler and linker determines how many sections there are, and there's some additional information that you can follow up on. The real goal that I want you to understand is that there's a whole bunch of headers that are in every single executable. And some of these headers have no value to a 4 kilobyte production. I'm sorry, but you know, at some point you decide, well, you know what, we can live without error checking. Oh, and that object I allocate, well, guess what? I'm not going to deallocate it. I'm just going to have to rely on the operating system to remove my object in memory. You start doing these things not because it's improper technique to do it. Of course, it's proper technique. You should clean up the things that you do, but when you're making a 4K, you're more interested in having that next scene having buildings in it than saying, oh, guess what, I deallocated everything I allocated and didn't rely on the OS, right? So the first approach that a lot of 4 kilobyte intro coders use is they use an out-of-the-box compression tool. And that basically takes your program and it compresses it. And to use another example, let's say that we have a living creature, and the living creature weighs X on a scale. So what this does basically is it decides to consume the living creature and store it in a lighter way. So it's like it replaces its blood with helium or something, and it basically just stores it in a compressed way. Then when you say, okay, I want my living creature back, it actually pulls it out, extracts it, runs it, just like it was the original creature. And I know that's kind of and so on, but essentially what you have is you have another EXE or image, executable image, that looks just like the original image when it runs, but it extracts itself to memory or to disk and runs it. So the program runs it, and you know, the hope is that the compression algorithm and the code is smaller when stored in that form. So we decided to take the sample, which remember it's at 11K right now, and to use UPX on it, which you can download. It's a SourceForge application. It's a very popular application. It's very well tested. There's versions for almost every OS out there on the planet. And we ran it through this. And we end up with a just over 6K production, which is a nice reduction. It gives us roughly 41%, which is still a far cry when you say, hey, well, you know, we need to get that magical 4096, right? Now, there's really one major disadvantage with this. Do you remember going back here when I said this stub and some of these things are really useless, right? I don't think a 4K intro developer is going to mind if their executable, when run in a DOS box, doesn't work, right? So we want to hack it slash and burn that. So this approach creates another Windows executable with the same DOS stub, or so, you know, to say, hey, guess what? I can't run this. So we really need to find a way of representing the code such that we don't have that problem anymore. So there's actually another executable image format that's supported by the Microsoft Windows platform. That's called .com. I don't mean .com in sort of the industry sense or the internet sense. This predates that. It's essentially a very small executable format that has no data, that has a maximum size of 64 kilobytes. And that's supported by the original DOS platform. And it can be loaded at basically hex address and so forth. So somebody said, okay, well, guess what? What I'm going to do, instead of writing a Windows executable, I'm going to write a DOS executable, and I'm going to tack on the Windows executable. And this DOS executable, what it's going to do is it's going to write to disk the Windows executable. It's going to run it, and then if it's being nice, it's going to delete it once it's finished running. So it essentially drops this executable to disk. Now you're saying, okay, well, wait a minute. You took this program. It's got, okay, I understand it's a Windows executable. It has this header, and then you're writing this other program that spits it to disk. This doesn't make sense to me. Well, the reason why you do that is because then you can compress the whole thing. And when you compress the whole thing, you've gone back and you've compressed, again with that chart, that header right there. So you can actually shrink down those strings and that code, and you end up saving on that header. It's not really elegant. It means that you have this little DOS box, pardon me, that pops up when it's run, but it does save a fair bit in the approach. There's several file droppers that you can use. For our testing, we used GEMS dropper, and we used APAC in order to compress it. So GEMS dropper, what it does is it took the Windows executable, it tacks on the DOS program as a .com file that writes it out, runs it, deletes it, and then we used APAC to compress that .com file into the smallest version possible. So you can see at this point, we've gone down to about 5K. So we're not quite there. but we're getting much closer. Now, one of the things that you'll have to remember, though, is it's merging these two things in uncompressed form as a program that's a run stub and the executable image afterwards. So, pop quiz, anyone who's really on the ball here, what does that mean about the largest uncompressible size of your production? What I mean by that is, what is the largest production that you can tack on to a stub and have it run as a COM file? Exactly. So you've got your overhead for whatever your stub is, right? And then you've got just, let's say it's, 100 bytes or so. Then you've got 64K less, right? That basically means that the largest production you could support with this and then compress is 64K because it shows up as a COM file. Very good. So writing to disk can be a problem. Some demo competitions actually don't allow you to do it. I remember I checked with, here's something that goes back. I checked with Assembly before entering in their competition to see if it was a permissible technique. We didn't use it because they said, no, don't write to disk at all. So we used UPX, and we had a very limited size that we could work with. And then that year, 5 out of the 10 productions all used file dropping. So it's a bit frustrating, and the rules have since been changed to accommodate it. Some compo rules say that you need to put it in the system's temporary directory, which means that you then need to have this overhead code which figures out where to write it to. And again, I mentioned the 64K limit as a bit of a test. So you can see that that may impact the ultimate size your production can be. So there's a very smart individual, a Hungarian individual by the name of, that goes by the demo scene by the name of M. And he realized two things. One is he realized that Windows has cabinet files, which are equivalent to, in Linux, you might think of them as gzip tars, or zip files. You can think of them as zip files, right? So there's this native inside the operating system file format that's supported with command line tools inside the operating system that you can access. Now, the real advantage of the real advantage of using that is that at that point, you've got an algorithm you can access without having to store the algorithm. You only need to store, hey, I need to uncompress this, and to call or make use of the algorithm. So it's built in. It uses LZX compression, which is also typically better than UPX or APAC. And the end result is there were two sort of phases to it. One was having a batch file that called the command line to extract the production from the cabinet file and then run it. So the size of your production then actually gets split into two different files. And your production size is the sum of that batch file, which is just a script file that says, I want you to extract this now, I want you to run this program, I want you to delete the file now. Or how do we get it so that it's a single batch file? And that's something that's also been done. So there's sort of two phases to it. One was to say, let's include a batch file that runs it, drops the cab file, does everything that's there, runs the executable, or later on there was a second phase that said, okay, let's find a way of combining these two together. So you can see I've got a sample script on the top right. I apologize for those that may be in the back having a little bit of trouble with it. But it basically says extract x.cab or extract 32, there should be a space there, x.cab. Now that's something which is operating system dependent. So WinNT, Win2000 called it extract 32, whereas 98 called it extract. So typically you'll see scripts that actually called both, saying, all right, we're gonna first call extract. If that doesn't work, well, I'll call extract 32. And so that basically means that you end up with a like a script that automatically has an error that already shows on the screen even before your production is running. Now, I mentioned there was a second phase of self-extracting, and this is based off Windows XP. And I won't get into the serious technical details on it, but if you're interested, I can certainly discuss it. But one of the things that happens is that when you try running a batch file in XP, essentially if it finds gobbledygook, it will seek once it finds a 0 character, it will actually seek to a certain character sequence, trying to run the rest of the batch file. So it has this error sort of coping mechanism, you could say, if it encounters a bad batch file. So the way that this typically works is that you create a batch file, you put the cab file in it, and then you put an end-of-line sequence into it, and then you put your script. So then you can actually extract your batch file. And that is very OS specific. Now, there's a very good tool by Mumak, another Finnish fellow, that is hosted on 24/4.net, the idea that you take 20 kilobytes and you shrink them down to 4 kilobytes. However, our production, which we started with, which was 11, only goes down to 4,906 bytes. Remember, our goal is to get underneath 4,096. So we're getting closer. Disadvantages. To support OS compatibility, you have to make multiple calls. And remember when I said you can do this nifty thing with the error coping mechanism of Windows XP? Well, guess what? You end up with this really ugly line right up there when that cab file runs. It's good compression, but it isn't context sensitive. So it interprets everything that you're doing the same way. And it basically sees your program not as a program with data and code and routines, but it sees it as a big stream of bytes and bits. And to really get beyond this was the de facto standard for probably the last, I don't know, about a year and a half, 2 years ago was the de facto standard. But to go beyond that is you need to get into the code generation itself. So there are tools that are replacing the linker inside executable generation. And that actually means that it can look at and understand your code and make a better type of compression, context-sensitive compression, specifically for your program. I also mentioned for any of the Linux gurus that I was going to try to talk Linux, so please forgive me if I butcher the OS. I really love it. I used to admin on AIX many, many years ago. So cab dropping for Linux, similar approach. You use gzip. The intro runs a shell script that extracts it, and I have an example here, which basically says, take the tail end, copy it out, make it executable, run it, delete it, and exit. So it's a single line, and the really nifty thing about this is that you don't end up with any of the sort of heart-stopping gobbledygook that occurs in the Windows platform. And you can read more about the cab dropping technique. So getting into the new linkers, the de facto standard in the 4 kilobyte community at this point in time is to use a tool in the Windows 32 platform called Crinkler. And that's sort of a play on words based on linker. And it was put out by the Blueberries and TBC, Mentor and Blueberry and
Those guys.
Those guys, thank you. I'm falling all over my Canadian accent, thank you. And you can find out more information on Crinkler.net. I should also mention there are some alternatives that are up in the wings. There is a link here for A-Link, which is alternative linker. And it looks like if somebody was, fairly entrepreneurial about what they wanted to do, they could also find ways of using that to reduce their size. But at this point, we break the 4 kilobyte barrier. We end up down to 2,457 bytes. Now, if that was all there was to it, we wouldn't have the productions that looked as fantastic as they are. So to show you, again, we mentioned that we're going to do the out-of-the-box techniques. I haven't altered the code in any way. I haven't changed the way it runs. It's still the same executable image. I've just changed the way it's represented. Aztec is going to talk about actually changing some of the inside the box in order to drive it even further.
All right, well, that part of the talk was supposed to be 15 minutes. It's actually been 30 minutes, so I got to really rush on this next part. All right. Basically, the compressors are limited. We were able to go from 11K down to 2.5K using the crinkler tool, which is impressive, but it only leaves 1.5K for music and graphics. It's not enough space to make something impressive. So if we really want to get down and make a good production, we have to trim that fat and get our code and our data down as small as possible so we can make a nice use of the rest of the space. So value size over maintainability and correctness. Be ruthless. There's no reason to be nice and, like he said, check for errors. You know, if an error happens, let it happen. Who cares? You know, your program crashes, you get a nice dialog box. So the first thing I'm going to do to make the program smaller is remove the C standard library. Every C program you compile gets this library in by default. It has two parts. It has a DLL that has a bunch of standard functions, printf, malloc, stuff like that. It also has a part that is the startup code. So when the operating system launches your application, it doesn't launch directly into your function. Instead, it calls this other function, winMain CRT startup, which does some initialization junk, calls static constructors if you have static objects, and then it launches winMain. So the first thing we can do is simply rename winMain to winMain CRT startup. That way, the linker says, oh, this is the real entry point, not the one in the standard library. Also, we can't call any standard library functions if we don't have the standard library, obviously. So in the nehel tutorial, she calls malloc on line, no, memset on line 215. So we have to replace that with some alternative code. Some compiler features also call into the standard library. So we can't, for example, do stack checking, you know, to make sure we haven't done a buffer overflow. So some stuff like that has to go away. If we do all these things and we remove the standard library from the linker options, we end up with a 473 byte reduction. So that takes us down to 2066 bytes. So it's a small savings, but when you consider that it's 400 bytes, it's almost 10% of the entire production right there. So it's very good. If you don't have a standard library, there's some tricks you have to do in order to code in C. You can't use library features like new and delete. Sometimes, if you have like a big structure and you set it to 0, the compiler will secretly call memset in order to do that. So you have to be very careful. Typically, the way you would handle that is by using static memory. I'll talk more about why that's good later. Also, big one is floating point integer conversion uses a routine in the standard library. So if you cast a float to an int, you have an explosion. So the way to handle that is you get a 4K math library, which contains inline versions of all the math.h functions, so you can still use those. And it also provides an F2L function, so you can do your floating point integer conversions. We include one of these in our package that goes with this speech. It'll be on the In4K site. Actually, I stole it from a guy named Chaos, and you can Google for it on the web. It's right there. The next thing I'm going to do is remove windowed mode. Now, in the nehel tutorial, he actually has a mode where it can be run as a window or as full screen. Well, it's a demo. It runs full screen. There's no need for that, so I go ahead and remove that. It has a switch that only renders when it has focus. Well, we'll just always render because it's a demo, and no one should ever be switching away from it. Until it exits, of course. Unless it sucks. But then you can press escape. Also, he has some code that says, no, don't start the screensaver. Well, I don't think there's any 4Ks longer than 2 minutes or maybe 5 minutes at the most, so screensavers aren't a big issue. He has some elaborate keyboard code. Well, all we need to do is check for escape key, so we can kill that. OpenGL state setup, he calls a bunch of functions that are purely redundant. Get rid of those. So just by removing obvious sort of stuff, we get a 520 byte reduction. So that takes us down to 1.6K. The next one is kind of controversial. We've been mentioning this over and over again. Remove error correction. So if you try to allocate a window and Microsoft Windows returns null, you're not going to give you a window. Normally you'd have a nice error box that says, oh, we're out of memory or something. But hey, if you try to use that null pointer, you'll just get this, your program has stopped working. Your program has caused, Microsoft will report the problem and, just some stupid generic error box because your program has done a seg fault. But that's okay. The user clicks close program and figures, oh, that demo didn't work.
That dialog box, by the way, is from Vista. So if it doesn't look familiar, that's Windows 98 was the blue screen, right? So then it was replaced with some other dialog boxes in XP. Now, of course, you've got Vista. And actually, one of the other things I'll mention is that as we go on, you can see in more and more the compatibility line changes, and that's why a good 4 kilobyte intro developer will release a 64 kilobyte version of their production called compatibility version, as opposed to 4K. So they show that they can do it in 4K, and oh, if it happens to be 5 years later, then you can run the compatibility version.
The other thing, too, is cleanup code. Now, if your program can crash and not bring down the operating system, you can leak memory and not bring down the operating system, too. It makes sense, right? So just leak everything. OpenGL context, window handles, memory, anything and everything you allocate, there's no reason to free it. Let the operating system do it. It'll clean up your mess and save some space. So we have a 406 byte reduction from removing the error handling, and we're running without protection, but I mean, hey, who cares? It works. So you can see the size is getting down by just removing stuff. Now we have to get into the realm of creative use of the Win32 APIs. Now this is probably going to be weird, but it works. For example, normally you register a window class and then use that window class to build your window. Now Windows has some built-in classes for things like buttons, edit text boxes, static controls. So we just use one of those as our window class instead. That saves a function call. Normally you call show window to show your window. Well, just use the with visible flag. Window messages. Normally you'd like to loop and process messages like resize the window or whatever, but all we're using the window for is to output stuff to screen. So there's no reason to process mouse input or keyboard input. Just simply don't even include the code. Also, because we're using a compressor, a 0 byte is typically smaller than a byte that has some random number in it. So anytime we can use a 0 as a structure field or a parameter value, that's a savings of bytes. So for example, instead of when you call create window saying, I want this window to be 800 by 600, use the with maximize flag and it'll just be full screen. Another thing, some structure fields you can leave blank, like when you go to create your OpenGL context, it wants a field that has the size of the structure for error checking or whatever. That one you can leave blank and it doesn't care, so leave it blank, save some space. Another thing you can do is store your stuff in static memory. In C, there's 3 places you can put stuff. You can put it on the stack, which is sort of the default location for new variables. So if you just create a random variable, odds are it's going to go on the stack inside your function. The other place you can put it is on the heap. So if you create your data using new or malloc, it's going to go on a place called the heap. Now those 2 places aren't that good because if it's on the stack, the C compiler has to allocate it. If it's on the heap, you have to call a function to allocate it. There's another place called the static data area. This is where variables that are declared with the static keyword go. It's also variables that are global variables go. And this is great because it's actually allocated by the operating system when it loads your program. So there's absolutely no code involved. So if you can get away with it, declare all your variables with the static keyword. It makes your code smaller. Well, experiment. Some variables helps and some variables it harms. But for like big data structures, always put those in static memory. All those techniques, the using the static window class and all that other stuff, gets us about 235 byte reduction. So now we're down to 1,005 bytes from the 2.5K we started off with before we started trimming the fat. You can do better. This is for the insane and the people who don't like sleeping at night. You can use assembly language. Now, the thing to realize is the compressed size is all that matters. The size of the code and the speed of the code don't really matter. Normally, a C compiler is way smarter than a human. Well, humans write that, but it's a computer doing the work and not us. Humans write stupid, recursive, repetitive code. It turns out that that's the kind of code compressors like. The sophisticated code that a C compiler turns out doesn't compress as well as a human's code. So just by writing it in assembly language, you get some pretty good savings without trying very hard. And if you do try hard, you can get even better savings. For example, if you explicitly use the same registers for the same tasks over and over again, the compressor learns about those patterns and just repeats them. I did it, and we got an 114 byte reduction. Not much, but if you're willing to try it, you can get some good savings over a sustained period of time, maybe enough to fit in another effect or 2. That's about as far as it's going to go. Let's start adding some stuff back in. We've got we've got over 3 kilobytes to work with. Let's add some music first. I'll talk about the music, and then Polaris will come back and he'll talk about some graphics. Now, your first reaction might be, if you've ever written a demo before, oh yeah, we'll use an MP3 file, get our musician to make some music for us, we'll get some artists to do some JPEG textures for us, we'll get some objects using a 3D modeler. Well, that won't work, right? Because JPEG's probably going to be 20K, your MP3 is going to be like 2 megabytes, and your 3D objects, I don't know how big those are going to be, depends on the complexity, but probably a couple 100K. So even with the best compressors, you're not going to be able to do it. Instead, what you're going to have to do is generate everything that you see in your demo using algorithms and code. So you'll find fractal algorithms online for generating textures that look nice. Use those instead of storing the same texture as a JPEG. All right, so when we start talking about audio output, we have to talk about how we're going to get the audio out to the speakers, assuming we know how to generate it. The typical way you do it in a 4K intro, because you're cheap and you don't want to spend a lot of space, is to do buffered audio. Basically, you create a big buffer that's enough space to hold 2 minutes of audio or whatever your demo's length is. You write all your music into the buffer before your demo even starts, and then you play the buffer back using something like play sound as a WAV file. Then the operating system's playing the sound, and then you start doing your graphics. The easiest way is using the wave out write function. There's also play sound, which is somewhat unreliable. And then there's direct sound, which can get very sophisticated with effects. So like you can get free reverberation effects using direct sound. But it's also a little bit more space consuming and harder to use. All right, the basis of any audio output routine is going to be something called an oscillator. Basically what it does is it generates a continuous waveform. The simplest one probably everybody knows about is the sine wave. So here we have a loop. It renders 16,000 samples. Each sample, we add a frequency to a counter, so this variable is constantly going upwards. And then we take the sine of that variable, the sine function, and then we add that into our audio buffer. And that creates a sine wave that sounds something like this. That sounds boring, and it's not very good, but you can experiment with other wave shapes, triangle waves, sawtooth waves, square waves, clipped triangle waves, all sorts of shapes. Another approach you could take is something called FM synthesis, where you use one sine wave to alter the frequency of another. So for example, you can create bell and drum sounds using this technique. Here I have the same counter plus frequency, so this variable is always going up. Take the sine of that makes an oscillator. And then this second oscillator down here, it's the same thing, except that the frequency is being adjusted using the first oscillator. So you can get some very interesting wave sounds with this. That sounds kind of like a bell, roughly. Now, if you really want high quality audio, the Windows operating system contains a file called gm.dls. And what you can do, open this file, it contains wave samples of various real instruments. So you simply load those samples up and play those back as your oscillator source. So you get high quality sounds of real instruments instead of doing some cheap sine waves or something.
And I'll mention one other thing in there. This is the modern day equivalent of those ancient, no, I shouldn't say ancient, older programs that was when I was originally first starting in the demo scene that would actually take advantage of the sound card's wave font data inside the card itself. So it would go to the sound card, said, give me the sound of a drum pack, give me the sound of this or that, and then it would mix it together in order to create a new wave. This is the same idea, but just done X amount of years later.
Although some people consider this cheating because you're using someone else's waveforms and not yourself. But hey, it's built into the operating system. It's not against the rules. So, all right. The next step, wherever you get your oscillators from, whether you do them yourself or you get them from gm.dls, is to do envelopes over them. Now, real sounds, they don't just cut in, play, and then cut off. A real instrument sound, you hit the string or you hit the drum. It comes in from silent up to loud rather slowly, and then it tends to decay over time, so it gets quieter with time. So in order to get good instrument sounds, you have to apply this sort of a amplitude envelope to the sound itself. So for example, here we have an oscillator. We multiply it with this envelope function before we write it out to the buffer. And the envelope function implements this sort of curve that generates a nice pattern. So if we do this to our bell sound, this is what we get. You can see that it has a very pleasant sort of beginning and an end every time it hits, as opposed to just sort of clicking on and then clicking off and just being silent. All right, now we've got some sort of sounds, not very good sounds, but they're sounds. Now we got to somehow play them back. We have to have a sequence of music, right? Musical score, notes written down somewhere, and then play those notes back. Typically what you'll do is you'll have a block of memory that contains your note data, and then you'll have some sort of loop that every time it sees a note, it writes it out to the buffer. Or you can hard code it like I did in this example. Normally you would never do it this way. One demo we did do, the Ethereum, was written this way. It worked, but our musician was pretty hardcore to be actually writing his music in C. Most musicians don't like that. All right, so that pretty much covers the basics of a synthesizer, a software synthesizer. This is about the most primitive you can get without sounding like crap. But the good news is you can make it much better. For example, you can use filters to increase certain frequencies or decrease other frequencies. You can use reverb and delay to add some sort of depth effects. There are many more. There's like compressors and equalization and all sorts of things. You can also give musicians more control, like because you're a coder, you probably don't have very good musical skills. Maybe you do, I don't know, but typically that's not the case. So musicians should be able to adjust basic things like the length of the note, the volume of the individual notes. Like the other sample didn't really address that. They should also be able to adjust like instrument parameters, like how much reverb we have, what frequency cutoffs we have, things of that nature. And another thing you can do to improve it is instead of rendering it all to one big buffer, which takes like 10 seconds of loading time before the demo starts, you can go ahead and render sample chunks and then play those chunks back in real time. But that takes more space, but I mean, on the other hand, it makes it somewhat nicer, so that's a trade-off. All right, this next part is up to Polaris, and he'll talk about object generation real quickly.
Okay, thank you.
That's my microphone.
So actually, it did remind me of how Dash4 did that music. Well, he wrote it all in C. I spent August long weekend writing it all in assembly and having him debug over the lake with his cellular phone saying, it doesn't sound quite right. I think you've got the assembly wrong. So that was a fun time. But again, just as Estek mentioned, you need to move from thinking about digital assets to algorithms. And this wireframe sphere model, which is a bunch of quads, has 4,800 vertices. We're talking about a program that has 4,096 bytes. A vertice is typically a tuple of 3 x, y, and z coordinates in which you may have, floats representing them. So you have 32-bit numbers, right? So if you do that, you end up with the raw model being 56 kilobytes, right? We're trying to have something in 4 kilobytes. So obviously you can't store the raw model. And if you're talking about using UV texturing, which is just a fancy way of saying having coordinates for putting a texture around the sphere, that balloons again up to 93 kilobytes roughly. So again, not possible. This texture here, which is a very basic texture, is 256 by 256. It's 24 bits, basically red, green, and blue, so 3 bytes, and its raw format is 192 bytes. So obviously storage is not an option, and we need to use algorithms. So this is a part of a texture generation algorithm that basically says, hey, if I'm sort of in this Y section, this X section, this Y section, this X section, it's basically testing to see if it's in one of these sections. And because this is 256 by 256, 128 or 128 is the middle line. And so we can see we're testing against the 128s and says, I'm going to make that white. So 255, 255, 255. And this code, albeit very simple, okay, it's extremely simple code. It is easily compressed, and it works out to be 160 bytes. So we can actually have a little program that, inside of an executable that takes 160 bytes to create that bitmap. It's also possible to do tessellation algorithms, which basically is a fancy way of saying making triangles or composing an object out of triangles with the 3D API. So here I have basically this being represented. I'm drawing the sphere now, creating all of those using some basic trigonometry. And that code, the very first part, rotates quads on an x-axis, and then it rotates it on the y-axis. So what happens is it draws each segment top to down. So it's going from zenith to nadir, so at the top all the way down. So I wrote that code, put some UV coordinates on it to create a bouncing ball of sorts. However, one of the most fundamental things you can't forget about, remember GMDLS, making use of the operating system? Well, again, know your environment, know your turf. So I wrote that code and it took 280 bytes. Sounds pretty good, right? Well, OpenGL has a code that basically is called, glue sphere. Make me a sphere. So all of a sudden, making use of that, it shrinks down to 145 bytes. So know your environment. And I wasn't trying to make the best sphere algorithm in the world, but the advantage of calling a library is that you only need the code to call the library. You do not need to have the code of the library. So with object generation, OpenGL and DirectX or D3DX have a number of primitives. So you have cylinders. You can think of those as tubes, cubes. Those can become buildings. You have spheres. Those can become planets, right? Disks, Pac-Man, etc. Teapot. I'm waiting to see a 4K with a teapot on it because to make a teapot in D3D, it actually has a teapot model, which is sort of a tip of the hat to the Utah teapot, which is a famous 3D model. But know where to use your algorithms and when to use the local system. Supershapes. There was a famous production called San Angeles Observation, thank you, which used supershapes. And this is an area where you may wish to use some algorithms. You can see you can create beautiful things with algorithms to describe objects. And you can think of them like, starfish, right? Spaceship, crazy bowling ball. Something that I dreamt last night and scared me because it was 4,097 bytes. So you combine all this together, and we have a miniature 4 kilobyte example. Our production takes roughly 1,426 bytes, and I've tiled the texture using a matrix, again, leveraging the code environment. So you can see we've got this little example. Maybe we'll do that again. What the heck? There we go. Right? Yeah. Now, one of the things which I will mention is like, okay, well, that's maybe a quarter of the size we got to play with, maybe closer to a third, somewhere between a quarter and a third. Remember, whenever you're seeing it, there is this critical mass of what it takes to put a production on the screen. Initializing the window somehow, right? No matter how sneaky it is, it still costs, right? Creating interfaces to the D3D or OpenGL interface, right? Doing all of those things has a bit of a critical mass.
I think Crinkler's base size, if you have a 0-byte executable, is like 500 bytes just for Crinkler.
Exactly. So with that, it means that there's so much more you can do beyond it, but you've basically got, at the end of the day, you've got a lot of space to play with. So that brings us to the end of the production. Just want to open it up for any questions. We do have a few quick moments for questions, and I don't think there's anything after us, so we can maybe push that a little bit for anyone that has any questions. So please don't be shy. In the back. The 4K math library was actually written by a coder, and what it does is it creates inline functions, so everything gets compiled into your source code in the smallest way possible. So you're not calling an external library, it's actually being built in. So pretty much anything that's on the... Yeah, that's actually cheaper on average. Yes, in the back?
Well, let me be specific. You have to link to OpenGL because otherwise you can't render anything using OpenGL. But the C standard library is mainly support routines for coding in C, things like malloc and printf that you don't really need. So removing that one is one thing, but some other things you do need. Like on my 4K that I'm working on, I think I have directsound.dll, I have opengl.dll, and wingdi.dll. Those are the three I have to link to just to get things going.
And another thing I'll mention is that there's tons of other tricks and techniques that we didn't even dive into. And I think that what happens is there's this sort of adoption routine. You figure out this dirty trick, and I do have some dirty tricks that I haven't used yet, so that's why I'm not teaching anyone them yet. But you figure out this dirty trick or this technique, right? So then you exploit it, and somebody says, oh, that's a dirty trick. Then X number of months later, everybody's using it, and it's become a standard technique, right? So I think that there are certain things that you may consider too risky to do. And one of those techniques is import by ordinal, which I'll say, and it's sort of frowned upon. You have a couple of different ways of pulling in libraries. So you have OpenGL or you have DirectX or what have you, okay? And you want to call a function to it. So you may have some code that goes to that library and says, give me function glue sphere, right? You may also have code that says, give me function 12. Well, obviously, having G, L, U, S, P, takes a little more space than 12. The problem is, though, is that the people that write these libraries sometimes change where things are. So 12 may suddenly become a box. So your sphere world, 4 kilobyte intro, with sphere particles or planets, suddenly becomes cube world, right? It's a mock example, but it's possible. Now, OpenGL actually, interestingly enough, says 12 is a sphere, and the standard says 12 is a sphere. So you may be able to take advantage of that technique, but other DLLs, such as DirectX or sound APIs and so forth, don't make the same guarantee. So that always comes back to somebody saying, all right, I'm going to draw the compatibility line here, and for everyone else that runs a new version of the OS that's been service packed this way or what have you, is going to have to run the compatibility version. So you have all these demo coders that are sitting there anxious to get to the compo machine in the hopes of testing their production to make sure they've got their ordinals right. And to be honest, I think at that point you've made a deal with the devil. It's a little too far for me. The compatibility line's a little too, on the left or on the right. It's a little too far from center for me. So that's where I would draw the line personally.
Statically. Yeah. Well, typically you know how much memory you need, right? I'm going to have 5,000 particles in this scene. Therefore, I need an array with 5,000 slots in it. So instead of saying new, array 5,000, you just say static array 5,000 equals 0, and then it'll be allocated by the operating system for 0 cost. Somewhat.
Yep.
Both.
Yeah. Actually, I'll show you. I'll compile one of them. We can compile one, eh?
Well, I guess you could.
Yeah, why not? Actually, maybe. Which one's the first one that has crinkler? Is it?
Yeah, it's nehel
Actually,
one.
you know what? It's a 0. We did crinkle this one. Yeah, there we go. Okay.
I think it crashes Visual Studio to open up Mac files. You have to right-click and open with Notepad.
Oh, okay, hang on. It's not the first time I've used the tool, don't get me wrong, but Guybrush, if he's in here, I'm logged in as you right now. So that's the reason why it's...
So basically, the gist is Crinkler replaces your linker. So it does a bunch of tricks as it builds your executable file. It has different header structures, does packs things differently. For example, when it imports libraries, it doesn't import them the normal way. It uses a technique called import by hash, which saves space.
And I will say that one of the things as well is you do not need, really outlandish tools. This is Visual C++ 2005, which is the Express version, so you can actually download that from Microsoft's site, and it does just as well as anything else. Okay, so this is the build. Whatever, okay. Hopefully this works. Okay, so right now it's performing the make file. It's created the link. Oh, dang it. Okay.
I don't think it was set up for linking properly.
Yeah, I think I know why. Hang on a minute.
Do we have any other questions? While he's doing that, I can answer some more if anybody has anything.
Have you guys tried out Crunchy?
You're thinking the far brush tool.
That's more designed for 64K. I think it gets better ratios, but it also has a higher header structure, so that the cost ratio is not good until you get up to larger sizes.
Is there pretty much a totally different model for 64K?
Typically, you don't need to do nasty things like getting rid of the C standard library. You can code more normally and not worry about it as much because you have more space.
1K is as big a deal.
Right. 1K of extra space, if it saves you a month of production time, that gives you more time to get more stuff in. Whereas 4K, it probably only takes you a month to fill up 4,096 bytes if you're working, at a fairly decent pace.
All right, that's the definition of foobar. Sorry.
Well,
I'll show you later. Yeah, okay.
he has. I think you said that the 6 compiler, Visual Studio 6 compiler, was not as small as the compiler from Visual Studio 2005.
Well, I think there's two things, because you kind of make this patch because you realize you do have to use a compressor, right? You saw that in the slides, that it just, as soon as you got into like the Crinker realm, all of a sudden you had something which was ridiculously oversized for the production into possible for 4K, right? Like it was, closer to 2K. Now with that though, means that even if you think of the most brilliant way of representing an algorithm that in assembly language would shave off 20, 30, 40 bytes, right? It then becomes suddenly that the patterns become less frequent. You may have less zeros in your code. So all of a sudden, these things that the compressor was easily able to represent in your naive or less elegant solution suddenly blow up, and you end up taking more space. So your uncompressed size can go down, and your compressed size can go up. So with that, it can be a bit of a challenge. But I have, usually what happens is that you start in C++ of some sort. On In4K, there is a gentleman in Scotland that goes by the nickname Old, from Old's Lang Syne. And he uses GCC a great deal. And that is something that he has a great deal of success with. And there's specific linking options that you can make advantage of and so forth. But at some point, you may also go to assembly language, which can require a fair bit of effort. The Northern Dragons hasn't released one in pure assembly in a long time, albeit most of our music code has been in assembly.
The one I'm working on is pure assembly. It's a nightmare. But on the other hand, it's very small, so it's trade-off.
So, yeah. And that's where I think that sort of the naivety of, hey, you know what? Let's make a small production. It won't be that much effort. Kind of wears, because when you spend your entire weekend creating, 10 pages of finely honed assembly language code to squeak out every single byte, you realize, okay, this was a whole different gig. I didn't know what I was signing up for. Now, of course, 6 years later, I'm still addicted to making them. So. Any other questions? So, going once, twice. All right, thank you. Oh, one last thing. There is what's known as Hugi. It is a disk magazine that is published. The lead editor is in Austria. It is a demoscene staple. They graciously all agreed, I'm also a member of Hugi's staff, that we would use Block Party as an event to release a one-of-a-time, first-time ever custom release on CD-ROM It's a PC application. You put it in, it auto runs. If you don't like that, just press Shift. And it will give you a dialog box. And it is a disk magazine, which means that it has an interface. It allows you to see it. It is not yet available on the internet. It will be tomorrow morning. But this is your Block Party exclusive, and they are beautifully printed, care of my own printer, which can print on CDs. So these are an exclusive thing. They don't even have them in Austria yet because I printed them. I took them with me. And I'm going to be sending them all over. The artist that did this is in Israel for the graphics. I mean, I've got this mailing list that's just ridiculous. But anyone who is interested, there's also, you can download, if you go to hugi.scene.org, you can download a Linux viewer. So with that viewer and the Hugi DAT file, you can view it on Linux if you so desire. So this can still be useful to you, and you don't have to press Shift to avoid the auto run. So anyone who would like to see that, please grab a copy from me or Radman. Radman's been flying around with copies. But please don't decide it's just a colorful coaster. Just take it if you are very interested in seeing the content. Thank you again so much for your time. Yes, it's in English.